So now let's talk about how this sodium and glucose Symporter works. As I have mentioned, most of the cells that actually import glucose, they express one transport protein called uniporter GLUT proteins. So this is the GLUT proteins, and most of the cases, most cells has glucose higher in concentration outside. Concentration of glucose is higher than inside, and GLUT proteins acts as a uniporter. It shows passive transport of glucose. This is case of most cells, but there is exceptions, and here the sodium and glucose Symporter plays the role. The first cell is called epithelial cells that line the small intestine. Basically, the brush border cell we call brush border cells, and in case of epithelial cells that line the kidney tubule. In these two cases, the scenario is different. In these two cells, what happens here? The concentration of glucose, suppose this is the concentration of glucose, outside is low and inside is high. See, these epithelial cells that line the small intestine, they actually line the lumen of the small intestine where dietary glucose is present. And these cells, suppose this is the cytosol. So inside the cytosol, the concentration of glucose is high because they absorb always the glucose from the small intestine lumen. So they absorb the glucose from diet. Okay. But in case of these kidney tubule cells, they actually resorb glucose from, remember this, ultrafiltrate, from ultrafiltrate, and from this ultrafiltrate they absorb glucose and make it urine. So ultimately the ultrafiltrate becomes urine. So our system, physiologic system, do not want to lose the glucose. That's why it resorbs from these epithelial cells that line the kidney tubule. So they have this sodium glucose Symporter to resorb this glucose in case of kidney tubules, and in case of epithelial cells, the lumen contains the dietary glucose that it absorbs. So absorption and resorption occurs. Now there is two examples of sodium glucose Symporters present. One is called SGLT1. These small intestine cells express SGLT1. The kidney tubule cells express SGLT1 and both the SGLT2. So see, our system does not actually permit the elimination of glucose from the ultrafiltrate to the urine. So that's why two Symporters are actually, both are SGLT1 and SGLT2 are present in the kidney tubule to resorb the glucose. So here basically what happens, as I have mentioned previously, that the outside of the membrane of all cells are actually positively charged, see, and inside is negatively charged. Okay, in resting conditions, okay, see, let's suppose this is the Symporter. So in case of this sodium glucose Symporter, this glucose actually present in the lumen of the small intestine or the kidney tubule, and it moves into the cells. So it moves into the cell. Okay. Also, we know that sodium present in higher concentration outside than the inside, so it will move inside the cells. Now this red movement is actually downhill movement, and this green movement of the glucose is actually uphill movement. So this is the downhill movement and this is the uphill movement. See, movement. So by moving the sodium down the concentration gradient or downhill movement, it generates energy to help the glucose to move by uphill movement. So uphill movement requires energy, but in this case the sodium concentration gradient, electrochemical gradients helping the glucose to move inside. So both this sodium and glucose will move inside the cells, and here sodium is actually showing the downhill movement. The concentration gradient will like this, the outside is the base and inside is the point, and in this case it will be the glucose, the chemical concentration looks like this. Okay, so here one thing important is that two sodiums actually moves inside with one glucose. Now I will show the mathematics or the formula how much free energy is generated during the movement of sodium inside, that drives the movement of glucose from uphill, from lower to higher concentrations. This has some formula. Let me explain. So basically what is happening here, through this Symporter, two sodium are moves inside and one glucose moves inside. So that's why it is called Symporter. Now, how much energy is generated by the movement of sodium inside that gives the energy to move the glucose uphill? We will calculate it. As I have mentioned, there is two driving force. One is called the chemical concentration gradient, and another is electric potential or membrane potential. We will take both these contribution of the driving force in case of sodium. So let's see. The free energy change we denote as delta G. For chemical concentration gradient we are writing it C. The formula is the free energy change of occurs during the import of sodium, because here the sodium concentration is high outside, so it will generate, the formula will be RT ln sodium, that is in concentration, and sodium divided by sodium out. So we have to divide the two concentrations, and I have mentioned that outside the sodium concentration is 145 millimolar and inside is 12 millimolar. Okay, so we will write this. Now the R is equals to the gas constant, and it is approximate 2 in value, but it is 2 in calorie. So we will convert this calorie into kilocalorie. So we will divide this whole equation by 1000, because to convert calorie into kilocalorie we have to divide this by 1000. So the value of R is, this is the gas constant, approximate 2. T is absolute temperature in Kelvin. So in Kelvin we actually add 273 with the degree centigrade. So whatever the degree centigrade we add 273. Now let's take examples of 25 degree centigrade. So we will add 273. So we will get 298 degree Kelvin. Okay, so we will convert this centigrade to Kelvin. So let's suppose at 25 degree centigrade, this temperature, this value will be 298. And this natural logarithm can be converted into log 10, and actually when we convert this natural log into log 10, we actually add another value, that is 2.303. So all this value will be divided into 1000. Okay, as I mentioned, this is the 2 is the value of calorie, so we have to convert it kilocalorie, so we have to divide 1000. Now in this case, for our simplicity, let's assume the inside and outside concentration difference is 10 times, because as you can see here the difference is approximately 12 times, because here is the outside is 144. Let's suppose 145 or 144 divided by 12. So if you divide, it will found that there is a 12-fold difference in the concentration gradient. More concentration, 12-fold more concentration outside than inside. So let's suppose not 12 but 10 concentration gradient to it will help us to actually calculate. So outside, inside is 1. Let's suppose and outside is 10. So this is the value. So what will happen? The log 10 of 1 by 10, suppose this is the 1 by 10, this concentration is equals to -1. Okay, this is the -1. So we will replace this with -1. Okay, so we will replace this with -1, this logarithm value, and here you will find approximate one value, so 1.4. So basically it will generate -1.4 kilocalorie per mole. That means when sodium, 1 mole sodium enters inside the cells, due to only the concentration gradient, it will generate 1.4 kilocalorie. The minus signs indicate that it will generate the energy. It is energetically favorable and it generates the energy. So minus 1.4 kilocalorie. So for 1 mole of sodium, it will generate 1.4 kilocalorie. This is only for concentration, chemical concentration. Now let's the value of electric potential. So let's take the value of electric potential. The formula here is the free energy change that occurs during this electric potential. Okay, so this electric potential will generate the free energy change when sodium will move inside, because the outside is plus charge and inside is negative charge. So it will allow, or it will actually permit the movement of sodium inside, because negative charge will attract the positive charge. So the free energy change will be delta GE. E for electric potential is the formula is ZFE. Now Z is the value of the charge of the solute. Here sodium contains positive 1 charge. This F is equals to Faraday constant. It is 23.06 kilocalorie. So we don't have to divide it. And E is equals to the electric potential at resting membrane potential, that is about -70 millivolt, but we will convert into volt. So it is about -0.07 volt. So we will multiply it -0.07 volt. Okay, so this value. So what will happen, if you multiply this, you will find -1.6 value, approximately 1.6 kilocalorie per mole. See, so by chemical concentration gradient, it is the sodium is actually generating, it will minus, sorry, here will be minus 1.4 kilocalorie per mole. So by chemical concentration gradient, the free energy will generate is 1.4 kilocalorie per mole. By electric potential or membrane potential at resting membrane potential, it will generate 1.6 kilocalorie per mole. So if we add these two values, we will find -1.4 minus 1.6, that means -3, approximately 3 kilocalorie per mole. So by moving 1 mole of sodium, we will generate 3 calorie per mole. Now let's see what will be the total free energy change when sodium and glucose both moves. So what will be the total free energy change? Let's see. We will write it delta G, that means the free energy change, and during this case both the glucose and sodium will be considered. So the formula will be RT-ln in case of glucose, that is concentration inside divided by glucose concentration in the outside. Okay, plus, as because two sodiums are moving, so we will write 2 and we will put the whole formula like RT-ln sodium, that is in, divided by sodium, that is out, plus ZFE with multiplication with 2, because two sodiums are moving and in this case one glucose is moving. Now this value, we know the value of this is actually minus 3 kilocalorie. I'm just writing 3, so it will be multiplied with 2, so we will find that this whole formula, obviously this will change into 2.303 into the R value is 2, the T value is 298. We have to divide this with 1000 and we will get the log 10 value of glucose in divided by glucose out. I'm just writing here out, in and out, and this value is actually 1.4, so minus, this will give minus 6, so here will be 1.4 log 10 in by out. This is very simple, you see. And one thing we have to understand is that we can measure the inside concentration of the glucose and outside concentration of the glucose by this equation also. If we assume that at certain concentration gradient of glucose, this whole process actually stops, this Symporter actually stops. This is called equilibrium conditions. At equilibrium condition, this whole functioning will stop because they will reach their concentration, chemical concentrations at which they will not move inside or outside. So this is called equilibrium situations. At the equilibrium situations, the chemical difference of glucose will be such that glucose will not move. The sodium electrochemical gradient will be such that it will not move. So the whole Symporter will stop working. And at that situation, we will put the value of free energy is equals to 0. So at equilibrium condition, we can take the value 0. So this is the whole number and minus 6. Now we will actually send this minus 6 to here. So we will get 6 is equals to 1.4, the logarithm of concentration of in and out of the sugar molecules. Now if we divide this, so we will get log 10 inside concentration by outside concentration is equals to 6 divided by 1.4, it is approximately 4.37. okay, such value will be. Now one thing we have to understand is we are actually trying to get how much concentration will be inside and how much concentration will be outside. Now this equation will show that the concentration of inside and outside, if the logarithm value is this, it will be 23000, that means 23,000 by 1. We can also assume it by flipping out, that means we can assume that outside concentration and inside concentration, then it will be helpful to us to understand 1 by 23,000. okay, just I am flipping the equations. So 1 by 20,000, now outside becomes 1 and inside becomes 23,000. That shows that when the glucose concentrations become 23,000 fold than the outside, then this process will stop. See how much efficient this Symporter is, that at the 23,000 fold of glucose concentration it can work. But what will happen if only one sodium moves through this Symporter? Then you will find only 150 concentration gradient can be created, because if you multiply 150 with 150, you will get approximately 23,000. That means if only one glucose molecule is moving, then it can only generate this glucose concentration gradient about 150. That means when the outside and inside concentration will become 150, it will stop. But because two sodium are actually moving simultaneously, that's why it can generate 23,000 fold concentration gradient of glucose. So by this way, we can understand how sodium and glucose Symporter